Chapter 4, Exponential and Logarithmic Functions, Section 4.5, Applications. In the previous section, we looked at techniques for solving exponential and logarithmic equations. Now we're going to look at some applications where we'll be required to solve such equations to obtain our solution. There are many situations where exponential and logarithmic equations will arise, so we'll look at a diverse collection of applications. We'll begin with a couple of problems involving compound interest. Example 1 says, how long will it take to double your money if it earns 6.5% compounded quarterly? Now, for this problem, we need the compound interest formula. So let me remind you of what that is. It's A equals P times 1 plus R over N to the NT power. P is the amount invested. A is the amount that the investment grows to, the future value of the investment. R is the interest rate. N is the number of times interest is compounded per year, and T is the amount of time in years. So it says, how long will it take? So we're solving here for T to double your money if it earns 6.5% compounded quarterly. So in this particular case, we have our interest rate R, and this should be expressed as a decimal, is 0.065. Compounded quarterly means the number of compoundings per year is 4. How long will it take to double your money means that the future value should be twice whatever the initial investment was. So if that investment was $100, then the future value should be $200. It actually doesn't matter how much money we start with. The only thing that really matters is the fact that it doubles. So whether it's $1 or $100, it should take the same amount of time to double the investment. So the question here is how long. So we're solving for T. So let's plug in what we're given here. A is going to be replaced with 2 times P. And then we have P on the right, so we're not specifying any particular principal or investment here. You could, if you wanted to, you could use P equals $1. That would be a simple way to deal with this problem if you wanted to, but you don't have to. And then we would have 1 plus 0.065. That is put over 4. And then raised to the 4 times T power. Now, if we divide both sides of the equation first by P, the P's basically cancel out. So they're eliminated. So we really only have one unknown here, even though P is initially an unknown as well. The unknown we want to solve for is time, and that's now the only unknown. If we compute what's in the parentheses, 1 plus 0.065 over 4, we can express that as a decimal. So let me just go ahead and do that now. That number would be 1.01625. So it'll be a little bit easier if we just write it that way at this point. Now, how do we solve for T? Well, T is an unknown in the exponent. We solve for what's in the exponent usually using logarithms. And in this case, as I did frequently in the previous section, I will use natural logarithms. So take the natural log of both sides of the equation. What that allows us to do then is bring the exponent down in front of the logarithm by applying the power rule for logarithms. So that gets the unknown out of the exponent. So ln of 2 equals 4t times ln 1.01625. Then we can simply divide to solve for t. We would divide both by 4 and by the natural log of 1.01625. So t should be equal to the natural log of 2 all over 4 times ln 1.01625. Then we can use a calculator at this point, making sure that we divide by all of 4 times the natural log of 1.01625. So when you do the division, the parentheses around the 1.01625 are not necessary, but the parentheses around the entire denominator, when you enter it into a calculator, should be included. So the outer parentheses that you see are mainly for the purpose of entering into the calculator. They don't actually have to be shown when you write the solution. But when we approximate this on our calculator, we get to the nearest tenth. I'm sorry about that. 10.8 years. So it should take approximately 10.8 years to double our investment under 6.5% interest compounded quarterly. Example 2 also involves compound interest. At what rate of return, compounded continuously, would your money double in 5 years? Now, the rate of return is the interest rate. So here we're solving for an unknown interest rate under continuous compounding. Now, with continuous compounding, there's a different formula that we use. That formula, if you recall, is A equals P e to the RT power. So it's a simpler formula actually than the general compound interest formula that we used in the previous example, sometimes called the PERT formula because we have P e to the RT. It looks like PERT. What is given here? At what rate of return, that means the interest rate is unknown. Compounded continuously, would your money double in 5 years? Okay, so the amount of time here is 5 years. And once again here we're doubling our initial investment, so our future value A would be twice the original investment, twice the principal P. So if we replace A with 2P and replace T with 5 years, and canceling the P because we can divide P out of the equation, we obtain a fairly simple exponential equation. 2 equals E, let's write to the 5R power, where R is the unknown. So this is an exponential equation because we have an unknown in the exponent. E is a constant. E is the base of the natural logarithmic function, about 2.72. So to solve for R, once again, we'll use natural logarithms. In particular, with a base of E, we should always use natural logarithms. So take the natural log of both sides of the equation. What happens in this case is that the natural log and E essentially cancel each other out. So we don't need the power rule if the base is E if we're using a natural logarithm. So on the left we have the natural log of 2. On the right we have simply 5R. So if we divide both sides by 5, we get R equals natural log of 2 divided by 5. Then we can use a calculator and approximate this. It's about to 3 decimal places, 0.139. So that would tell us then that our interest rate would have to be approximately 13.9%. Our next example, example 3, involves the method of radiocarbon dating, where a radioactive isotope of carbon, carbon-14, is used to date certain artifacts. These are artifacts that contain carbon, so they would have organic material within them. So things involving, for example, wood or bone, something that has organic matter. This method can be used to date those artifacts, and the principle involves the half-life, the known half-life of carbon-14 being approximately 5,700 years. So that can be used to determine the age of the artifact, and I'm going to show you how that method works and how we can use exponential equations to solve such a problem. I may have to split this between this video and the next video. I probably won't have time to finish it. Let's read the problem. The half-life of carbon-14 is approximately 5,700 years. King Tutankhamun of Egypt, King Tut, died in 1346 BC. If an artifact was made at the end of King Tut's reign, what percent of the original amount of carbon-14 should remain in the year 2014? Use the exponential model. A of t equals A0 e to the kt, where A of t here represents the amount of carbon-14 after t years. What we're going to begin by doing here is determining the decay constant, k, which is a negative constant. So anytime you're dealing with exponential decay, the constant k should be negative. We're going to determine what that is first, and what we're going to do is use the half-life of carbon-14 to determine the decay constant k. The principle that's used would be that the amount of carbon-14 present, A of t, after the half-life elapses, that is, at 5,700 years, A of 5,700 is 1/2 of whatever the initial amount A0 would have been. And here we can leave that as an unspecified quantity. 1/2 of whatever the original amount was, and we don't know what that amount actually was, so we'll just leave it as A0. Now, if we substitute that into the expression A0 e to the kt, what that gives us is A0 e to the k times 5,700. Because we have A0 on both sides of the equation, we can divide it out. So that disappears. So even though we don't know what A0 is, we can just eliminate it from the equation. Our resulting equation then is 1/2 equals just e to the 5,700 times k. This is a simple exponential equation that we can solve using natural logarithms. So take the natural log of both sides. This is similar to the previous example we did with continuously compounded interest. ln of e to the 5,700 times k. Then we have ln of 1/2 equals, and then on the right, ln and e cancel, leaving us just with the exponent of 5,700k, and then dividing both sides by 5,700, we have k equals the natural log of 5,700. Sorry, I made a mistake. I should have said the natural log of 1/2 divided by the half-life of 5,700. That turns out to be approximately negative 0.00012. I'll continue this problem in the next video.